It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen, like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do. Some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth mountain valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about minus 300 Fahrenheit on Titan. So things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, The Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons. So we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface in a lake, for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere. That's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it. And so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes, also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy, and they rotate. But there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone. And that's a region of very calm winds and no clouds. And usually has a size of about 10, 20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the